Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Tepang Mapotani. This lesson is brought to you by the Northern Cape Department of Education in collaboration with Pagama Research and Development. Now, grade 12, in today's lesson, we turn our attention to paper 1 revision as we are preparing for our June examination. And for this revision, we are going to focus on trigonometry. And remember, trigonometry weighs around 50 marks in our paper. Now, by the end of this lesson, grade 12, you must be able to identify the structure for paper 2, and we are focusing on the topic of trigonometry. Now, grade 12, remember, this is our structure for paper 2, and we are saying paper 2 has statistics, analytical geometry, trigonometry, Euclidean geometry, and measurement. And remember, for our June examination, we are not going to focus on the statistics. All other topics that appear there, they will form part of our examination. And remember now, this weighting, it is based on the full-blown exam paper. So the weighting might slightly change when we are going into our June examination. So the topic for the day, it is trigonometry. And trigonometry, it is usually allocated 3 questions. In most cases, trigonometry is found in question 5, in question 6, and question 7. Right. Grade 12, we have question 5.1. And for this question, grade 12, you are given 5 minutes to complete this activity. And your 5 minutes starts now. Welcome back, grade 12. Let us now go through the solutions to this activity. Now, in 5.1, we are given that sin beta is equal to 1 over 3, where our angle beta is an element of 90 and 270. So for this question, we are saying, without using a calculator, determine each of the following. Remember, to work with this kind of a question, where they say, without using a calculator, we are now required to utilize a Cartesian plane. So we have to draw a basic right angle triangle on a Cartesian plane. This is how we draw the right angle triangle on a Cartesian plane. Remember, we are going to utilize our soccer tool. And we remember very well that on our soccer tool, we are given the angle of sine. Then we know that sine, it is opposite over hypotenuse. Now, if I check, I have sine beta, which is 1 over 3. This is opposite over hypotenuse according to our soccer tool. Again, if you plot this in our Cartesian plane, you will remember that this will give us y over I. That is our right angle triangle that we're going to draw. Then you notice that y corresponds to 1. So the y value in this case is going to be 1 when I draw my sketch, and our r is going to be 3. Now, how do I know which quadrant am I going to utilize? The first thing that we're going to look at, we're going to look at the given sine or the given angle of sine beta is 1 over 3. If I can see my 1 over 3 is positive, meaning the solutions are found where sine is positive. So if I draw my Cartesian plane, you know this is a cast diagram. And we know that sine is positive in the first and the second quadrant. So that is where our sine is positive. However, due to the restriction says the solution, it is restricted between the 90 and the 270. So this is where we can now pick our second quadrant as where our solution is going to fall. As our first quadrant, where sine is positive, it does not fall within our restriction. So now we are saying our right angle triangle, we are going to draw it on the second quadrant, and we are now going to do what? We will now place in what we are having according to our equation given, where sine beta is 1 over 3, then 1 corresponds to the value of y, and 3 corresponds to the value of r. Then how are we going to find the value of x? To find that value of x, we are going to utilize Pythagoras. We will know that our x is going to be the square root of It's going to be a square root of 3 squared minus 1 squared. Then we get our x is equal to the root of 3 squared minus 1 squared. So we know that our 3 squared is 9. 9 minus 1 squared, which is 1 squared is 1. It's going to be 8. So our answer is going to be root 8. Remember, if I introduce the square root, it is a plus or minus. How do I know whether it's negative or positive? I can see by looking at my diagram that it is drawn on the second quadrant where x is negative. Therefore, our value of x is going to be negative root 8. So that is how we decide whether it's negative or positive. Now, after we do this, we can now find our value of cos beta. We now know that cos beta is going to be what? Our cos beta is going to be x over r. Then our value of x is negative root 8 all over. Yes. To find the value of cos beta, remember we say our cos beta is going to be x over r. Now, we know that our x, we found it to be negative root 8. So our cos beta is going to be negative root 8 all over our r. It was 3. And if we can further simplify our negative root 8, we're going to get our cos beta as negative 2 root 2 all over 3. However, you can just leave it as it is here. You are going to get all of your marks. Let's proceed. Now, let's look at 5.1.2. 5.1.2, we are required to find sine 2 beta. So what are we having here? Our angle, it is given in terms of beta, and we are now required to find the sine of 2 beta. How do we find sine 2 beta? So what we're going to do here is the following. We need to expand our angle in terms of a double angle, because we are given a double angle of a sine instead of just an angle. Because remember here, beta and sine 2 beta are not the same thing. So we need to expand sine 2 beta in terms of a double angle. When we expand it, we get sine 2 beta. It's equals to 2 sine beta multiplied by cos beta. There we can see now we have sine beta and cos beta. We no longer have a double angle. Then what do we do from here? We can now substitute our sine beta and our cos beta in those spaces. Our sine beta already, it was given from the question. So it is 1 over 3 into our cos beta. We found it on the previous question, or you can still say root 8 or negative root 8 over 3. Then from here, we are now going to simplify what we are having. Then we're going to multiply the two brackets. And we know that's going to be 1 multiplied by negative 2 root 2. It becomes negative 2 root 2 on the numerator. And on our denominator, we are having 3 multiplied by 3, which is 9. Then when we further simplify with the 2 outside, then we can say this is still over 1. Then 2 multiplied by negative 2 becomes negative 4 root 2 all over 9. And that's how we're going to find our sine 2 beta. Remember, when we're given a double angle, and the angle that we're having in a question, it is just an individual angle, you are supposed to expand that double angle. Let's look at 5.1.3. We are now required to find cos of 450 minus beta. What do I notice here? I notice that 450, it is way above 360. Then what do? We need to reduce this using the multiples of 360. We can use 180, we can use the actual 360 to reduce this. So 450, what am I going to do from our sketch? We are going to reduce it with 350. We are going to just say the 450 is actually, it's 360 plus 90. So 360 plus 90 will give us the 450. So what we say here, we can also just take 450 and we can minus the 360, then we get 90. So we got cos 90 minus b. That becomes easier to work with. Then what we say now, we can now see that what we are having now, it is what we call the co-functions. When we're having the co-functions, we have a co-function of cos 90 minus beta, we're going to go to our Cartesian plane. We're going to remember this is where 90 is. 90 minus our cos is positive. Then we can now see that the cos is going to change to the cofunction of sine. Then we know that we're going to have sine beta in this case. Then our sine beta, it was 1 over 3. Now, grade 12, we have question 5.2. And for this question, grade 12, you are given 10 minutes to complete this activity. And your 10 minutes starts now. Welcome back, grade 12. Let us now look at 5.2. 5.2, we are given cos to the power 4 x plus sine squared x multiplied by cos squared x. The first question says 5.2.1, we need to prove that cos to the power 4 x plus sine squared x multiplied by cos squared x over 1 plus sine squared sine x is equal to 1 minus sine x. Now, how do we prove this one? Now, we are going to pick up the side that is more complex. If we can check between the right-hand side and the left-hand side, because this side is left-hand side, and that side, it is a right-hand side. So we can see that the left-hand side, it is more complex. So we need to pick up that left-hand side, and we are going to work and simplify the left-hand side. When we are looking at the left-hand side, I'm going to look at the numerator, and I look at the denominator. What I see on the numerator is the following. I can see that we are having cos squared x as a common factor. Remember, grade 12, if it is hard for you to see that cos squared x is going to be our common factor, we can always look at or refer this to our algebra. How do we go to the algebra? We can actually make this cos to be x. So we can say it's x to the power 4 plus maybe our sign, we can make it y, then y squared multiplied by, then we have x to the power 2. So if we can let cos x to be x and sin x to be y, we can be able to see that when I look at my numerator alone, I can see that I can pull out x squared as a common factor. And when I pull out my x squared as a common factor, I am going to remain with x to the power 2 plus y squared, because the y squared, it is not common. Then that is what I'm going to remain with. So this is what I'm going to do. We can see that x squared is actually our cos squared x. So we can see that cos squared x, it is going to be our common factor. I pull out cos squared x as a common factor. I remain with, for the first term, I will remain with cos squared x plus sine squared x multiplied by 1, because I'm going to get 1 right there after getting that out. Then from here, I can now apply my square identity. When I apply my square identity, I remember that cos squared x plus sine squared x, it is actually just equals to 1. So what I am having on top, it is that when I apply my square identity, I will have cos squared x into 1 all over 1 plus sine x. Then what do I see? Let us have that again. We're going to have cos squared x into 1 all over 1 plus sine x. What do we see here? We see that we're supposed to have our solution in a certain ratio, which is the trig ratio. So in this case, we are going to either convert one of the ratios to be sine or one of them to become cos. So they must be the same ratio in this case. But then how do I decide where am I going to go? You can just look at the right-hand side and say, okay, my right-hand side is going to guide me. Then I am going to convert my cos squared x into what? Into becoming a sine, so that I can work with a one or a single trig ratio, which is one trig ratio, which is now sine. Then what am I going to do? I am going to utilize the square identity to now convert this cos squared x into 1 to become what? To become a sine. Then how do I do that? Remember, cos squared x plus sine squared x is equals to 1. If I transpose my sine squared x, I get my cos squared x. It's equals to 1 minus sine squared x. Right. So what I can see is that instead of having cos squared x, I can actually just have 1 minus sine squared x. That's what I can work with right there. So that's what I did here. I have worked with my square identity on the numerator. Then I have converted that to sine. Then what do I see after that? I can see that on my numerator, I still have the difference of two squares because I have one is a perfect square and sine squared x, it is a perfect square. So I can simply factorize the top part or the numerator using the difference of two squares. I get 1 minus sine x into 1 plus sine x all over 1 plus sine x. Then again, I can see that 1 plus sine x and 1 plus sine x, they will now divide out. Then I will remain with my left-hand side as 1 minus sine x. Then this is therefore, we can now see that my right-hand side also, it is 1 minus sine x. Then we can now conclude that the left-hand side, it is equals to the right-hand side. Now, let's look at 5.2.2. It says, for what values of x in the interval where x is an element of 0 and 316 is our expression undefined. How is it undefined? It is undefined. Remember, if we're having an undefined solution, it is when we are now having the denominator being equals to 0. So we are now saying, if the whole of this denominator, it is equals to 0, then we are now saying, our whole expression is going to be undefined. Then from here, we just have to solve for that value of x. Now, to solve for the value of x, we can now subtract 1 both sides, which is this one, or we can now say the simpler way to think about it. We can now say transpose that positive 1 to the right hand side. Then we have sine x is equals to negative 1. Now, remember, we are now having a general solution. We can apply the general solution in this case. And in this case, when we apply the general solution, we can also look at the Cartesian plane. And we're going to find the reference angle. My reference angle is sine, or second function of sine 1, it is 90 degrees. And we are working within the restriction of 0 and 360. Where is sine negative? Remember, this sign also will tell me where is my function negative. So the sine is negative on the third and on the fourth quadrant. So that is where I have my sine to be what? To be negative. Now, what do I now do in this case? We can now see that our sine is negative where on the third quadrant. What do I have on my third quadrant? I have 180 plus theta. That means from my reference angle, where I can just say x is equals to 180 minus the reference, which is 90, plus k, which is k times 3, 16. Then my x, which is the general solution here, it will become 270. However, we are already given the restriction. Because we are given the restriction, we do not need to multiply with the k and the 360 because we are given the restriction. Then x is going to be 270. Or another way you can think about this, it is to draw a function of sine to 360. This is my 360 from the 0 there. And we now notice that at 270, so that is where my solution is. When y is negative 1, this side it is 1. So when we're having the negative 1, at negative 1, the solution is 270. So that's why we pick up that 270 as our solution within that restriction. Write down the minimum value defined by this function. Remember, when you are looking for this minimum value, you must remember that from this equation, we have already established that the whole of this equation, it is actually equals to 1 minus sine x. So that's what we are working with in this case. Now, how do we now get the minimum value? Remember, don't be tempted to go and differentiate. Now, the best thing to do this one is to find the minimum value. We need to make this value to become the biggest. So to make it to become the biggest, I can look at my sine graph. When I look at my sine graph, the maximum value, the biggest value I can get, it is when that sine graph it is at 1. In simple terms, I can have y, it's equal to 1 minus sine x. In the space of sine x, I substitute in 1. Then y will become 0. So it's going to be minimum at y is equal to 0 in this case. So therefore, our minimum it is at 0. Why? Because I need to get my function of sine to be at the biggest value right there. That is my minimum value. Remember, that becomes my minimum value right there. Now, grade 12, we have question 5.3 and question 5.4. Now, for these two questions, grade 12, you are given 10 minutes to complete these activities. And your 10 minutes starts now. Welcome back, grade 12. Now, let us look at 5.3. Now, 5.3, it reads as follows. We are given cos into a minus b is equals to cos a plus sine a multiplied by sine b. We are going to use the above identity to deduce the identity that says sine into a minus b is equals to sine a multiplied by cos b minus cos a multiplied by sine b. Now, how are we going to do it? We know that sine a minus b, which is what we are working with, is actually equal to, if we can check this one, we are going to utilize the concept of the co-functions. Because remember, the co-function of cos, it is still sine. So I haven't changed anything in this case. So if I can now work this around, it's going to give me back sine a minus b. Because the co-function is going to change to sine, then I will still have sine a minus b. So that's what we're utilizing. We are going to utilize the co-functions around the sine to say, if I do it this way, I'm still not changing anything because the co-function of sine becomes the cos. Then what do? We are going to separate the a from the b. When I separate, I just distribute the negative ones on the a, then I will still have the b remaining with that negative into the negative. Then what do I see now? I have the first angle, I have the second angle. So I have two angles that I'm going to operate with. When I have those two angles, I can now apply what was given. What do I see? I have the first angle subtracting the second angle. So the rule says it is actually cos A, cos B, sine B. So it simply says now it's going to be cos of the first angle multiplied by the cos of the second angle, which is b, negative b in this case, plus, because it says the rule says plus in this case, plus sine of the first angle. My first angle, remember, it is 90 minus a, multiply the second angle, which is negative b. That is my second angle. From here, I can now reapply the concept of co-functions. I'm going to apply it on cos 90 minus a, and I'm going to apply it on sine 90 minus a. When I apply the co-functions there, I notice that co-function of 90 minus a becomes the sine a. Then I know a cos into a negative angle will become a positive. So that's why I have positive cos right there. Then when I proceed, I'm going to now focus on the co-function of sine 90 minus a. Remember, 90 minus a, it is on the first quadrant, sine is positive, and the sine will change to cos. Then the sine will become cos a, multiplied by sine into negative ab, which is a negative angle, it becomes negative sine beta. Therefore, I can now multiply the negative and this positive right here. Then I have my sine A multiplied by cos B minus cos A multiplied by sine B. Therefore, I have already now made that deduction in terms of that identity. So we can see how we prove the compound angles. We are going to be given the identity to use, that we are going to utilize an identity to prove another identity. Right. Let's move on. Now let's look at 5.3.2. 5.3.2, it reads as follows. Hence or otherwise, determine the general solution of the whole of this equation, which is sine 48 multiplied by cos x minus cos 48 multiplied by sin x is equals to cos 2x. Before we can proceed, what do you see? There is one angle. There's that angle again repeating itself. There's another angle. There's another angle. What do I think of? I need to think of the compound angles. Where do we think about compound angles? We think about compound angles grade 12 whenever I'm having one angle repeating itself and another angle repeating itself, then we can now think of the compound angles. And when I look at those compound angles, I can see that I am working with what? I am working with the compound angle for sine. Then when we look at the compound angle for sine, if you go to our formula sheet, we notice that our sine, let's say for example, we have sine A multiplied by cos beta. So the sine will be maintained as minus sine B multiplied by cos, or we can just say sine A is sine B multiplied by cos A in this case. And this is going to give us our compound angle of sine into A minus beta. So that's what we are looking at right here. So we can see there is one angle. We can say it's angle A. This can be angle B. Again, it's angle A. And this can be angle B. So that's what we are working with right here. Then what we do from here, we know it's a compound angle for sine. So we go to have sine into 48 minus x is equals to cos 2x. But the cos 2x, I cannot work with it. So what do I do? I can now try to change, because I'm having two trig ratios at the same time. So the best thing to do right here is to do what? Is to now change to a single trig ratio that we can work with. Similar trig ratio. Either we can change the sine to cos or the cos to sine. The easier way to do it is to change this cos into a sine using the cofunctions. When I do that, I know that the cofunction of a cos is sine. So I have sine into 90 minus 2x. What do I have? I can simply just look at it in this way. The sine and sine will now take out each other, divide out. I'm going to remain with my angle. You can just call it theta. It's equal to my reference angle. So those are the two angles I'm remaining with. I have the theta and my reference angle. From here, I am going to work with my general solution. When I work with my general solution, we are going to find a quadrant where sine is positive, because my reference angle here becomes positive. So what do I see in this case? Remember, sine is positive when theta is equals to our reference angle plus k times 360, which is the first quadrant. And sine is also positive when on the second quadrant where theta, so this is the quadrant, when theta is equals to 180 minus my reference plus k times 360. That is where my sine is positive, because my reference angle, if I can notice here, it is positive. Then my theta, I said, our theta is 48 minus x. So our theta, which is 48 minus x, we are having it there. It's equals to the reference angle, which is 90 plus minus 2x. So this is my reference plus k times 360. That is the solution in the first quadrant. And the final solution in the first quadrant, we are going to now work around that solution. And we know when it transpose the 42, it now becomes 90 minus 48, it becomes 42. Then we have the negative x, and we have negative 2x in this case, then what do we do from here? We are going to divide by the negative. We're going to transpose the negative 2x first, then we divide by negative x throughout. Then that's what we are going to get. Or when we transpose the 2x this side, we are going to have negative x plus 2x, and that will give us x, which is the x that we're having right here. Then the 48 minus 90, it gives me 42 times k, which is into the 360. Or let's look at the solution in the second quadrant. This is quadrant 2. On my second quadrant, we know our theta is equal to 180 minus reference. So it's 180 minus our reference, which is 90 minus 2x, plus k is an k multiplied by 360, where k is an element of real numbers. We must also, or integers in this case, right? So we must also indicate that k. Then from here, we are just going to now solve for the k in this case. What are we going to have? On my right hand side, I'm going to now have 180 minus 90, it becomes 90. Then I will have negative x, it's equals to 90 minus 48 minus 2x plus k times 360. Then from here, what do? We are going to have negative x minus 2x, because remember x and x negative, and the negative 2x is going to give us positive 2x, is equal to 42 degrees plus k times 360. Then from here, what do I now do from here? Now I can say negative x, negative 2x, it gives us negative 3x. It's equals to 42 degrees plus k times 360. Then from here, now greatest from here, what do we do from here? We are going to divide by the negative 3. When we divide by the negative 3, we notice that our x is equal to divide by negative 3, divide everything by negative 3. Then it becomes our x is equals to 42 divided by negative 3 is equals to 14 minus, where we are having 360 divided by negative 3, it gives us 120. Where k, so we produce that restriction right there. Now, let's look at 5.4. Now, for 5.4, we are required to simplify sine 3x plus sine x over cos 2x plus 1 to a single trig ratio. How do we now work at this one to become a single trig ratio? The first thing that we notice is the following. I have a double angle, I have 3x. Now, to work the 3x, remember we don't have a triple angle, for example. We are supposed to break that 3 into the double angle and a single one, which is now 2x plus x. Remember, our 2x plus x, it gives us 3x. I haven't changed anything from here. Then if we can see right here, we are having a compound angle for sine. Then we're going to expand it in terms of the compound angle. So it's going to be sine, which is with the first angle, which is 2x, multiplied by cos of the second angle, plus cos of the first angle, multiplied with the sine of the second angle, plus sine x, which is what we're having. So we can see that this gave us that compound angle right there, plus sine x. Then on below, on my denominator, I can say I'm working with sine. Then I'm going to convert that into a double angle of cos in this case, right? Thereafter, what do I do from here? What will we do from here? We are going to expand again the 2x again into a double angle. Then when we expand into double angle, we have this one. It becomes 2 sine x multiplied by cos x multiplied by the cos x plus cos 2x multiplied by sine x plus sine x all over 2 squared x in that case. Right. Thereafter, we can now take out the sine x as a common factor. When I take out the sine x as a common factor, what we remain with? We are going to remain with, so if I take out sine x as a common factor, we will now remain with 2. For the first term, it's going to be 2 cos. Cos and cos will give us cos squared x plus cos 2x plus 1. Right. All over 2 cos squared x. So this is what we are getting from taking out sine x as a common factor. Then from here, I can convert this double angle of cos. When I convert the double angle of cos, remember, cos 2x is actually equals to 2 cos squared x minus 1, which is actually what I dealt with here, and the 1 and 1 will they have subtracted out. Then this is why I'm having my double angle of cos. Then the 1 and 1 will also subtract out. Then when we proceed, in this case, let us now simplify it further. We are going to remain with sine x into, we're going to have 2 cos squared x plus 2 cos squared x all over 2 cos squared x. Then from here, what we'll do is the following. We can see that 2 cos squared x and 2 cos squared x, we can add them together. So we have sine x into 2 plus 2, it becomes 4 cos squared x all over 2 cos squared x. Cos squared x and cos squared x will divide out. Then I will remain with sine x into 4 divided by 2, it becomes 2. Then this becomes 2 sine x, which is what I am having right there. So that's how we work around that 5.4. Now, grade 12, I'm going to give you a minute to copy down this part of our question so that we can also focus our attention to the questions on the next slide. So just 1 minute to copy down this. Right. Now, let's also now look at the questions. Now, copy down the questions in relation to the sketch, and you are given only 10 minutes to work around the solutions on question 6. This question 6, remember, we have it from our November 2022. So your 10 minutes starts now. Welcome back, grade 12. Now let us look at question 6. Now 6.1, we are told that in the diagram below, the graph of f at x, which is equal to tan x, so we can see there's a tan graph there. So you must be able to identify that tan graph. So that is my tan graph, the one that I'm highlighting nicely there in red. And our g at x is equal to 2 sine 2x. So it's a sine graph, as you can see there, are drawn within the interval where x is an element of negative 180. So it starts from negative 180 to positive 180. And we have a, which is 60, and k, b are the 2 points of intersection of f and g. Write down the period of g. Where is g? G is my sine graph. How do we write the period of the sine graph? Remember, the period of a sine graph, it is equals to 360 divided by b. What we have? Sine bx. So that is where we are looking. It says a sine bx. So my period is going to be 360 divided by the b right here. So what do I think? From my question, I have my g at x, it's equals to the sine 2x. Then my b is equals to 2 in this case. So my period is going to be 360 divided by 2. Then my period in this case is going to be how much? It's going to be 180. So 360 divided by 2 becomes 180. So that's how I find my period. 6.2, calculate the value of k. Where is k? K, it is then found on the coordinates of A, where F and G are intersecting. So remember, I can use either F or I can use the G to find the value of k. Now, easily I can use y equals to sine 2x. Then we're going to substitute a point, which is A in this case. And when I substitute our point, then we can now say our y is k. So it's k is equals to, in the space of y plus k, is equals to 2 sine our a x. Remember, this x is to y. Our x is 60. So it's 260 times 2. Right. Remember, it was sine 2x. Right. Then we know that our k equals to be root 3. So if we can now write it properly, it's k, it's equals to 2 sine 2 into 60. That is where we get our k is equals to root 3. So that's our k right there. Now, look at 6.2. 6.2 reads as follows. On 6.2, we are now supposed to find the coordinates of P. Where is P? This is where P is. It's another coordinate of the intersection right here. So if I can work with symmetry on the same intersection, I can go back here in this case, and I go back with a, looking at the x-axis alone, I'm going back to 0, which is the 16, and I skip again with the 16, I get, which is negative 16. I move to that point of intersection again, another negative 60 unit. So what we see then, from 0, negative 60, negative 60, it is going to give us negative 120. So we can see how we found that value. We can find it using the symmetry, because we can see that it is now catching on the symmetry points of 60. If I can get there to the 60, from here to here it's 60, and from to another point again it's 60. If I had another point of intersection, when I repeat the graph, it's going to be again my negative 60 in that case. Then we can now see we're from 0 to that point of B, it is negative 60, negative 60, which is negative 120. Then our B is going to be negative 120, and K. Then our K, remember, it was root 3. So the value of Y did not change. Only X was changing in terms of that point. Write down the range of 2 times G at X. How do we now write down the range of 2 times G at X? The first thing that we do is to write down the range of G. Where is my G? Remember, my G, we are having a Y, it's an element of Y. Our Y is an element of negative 2 and 2 in this case. And how do I get that my value is 2? Because from my function, G at X, I have my function, it is 2 sine 2x. So my value of A, it is equals to 2. So 2 is equal to the minimum and the maximum. So this point here is 2, and this point here it's negative 2. So that is where I get my range to be between 2 and negative 2. Now, to get the range of 2x, what 2g, we're going to say we just multiply the range by 2. Remember, 2 times g at x, it means everything about the g at x multiplied by 2. So on my g at x, I'll have negative 2 multiplied by 2. And also on the second value of y again, I'm going to have that 2 multiplied by 2 again. So everything multiplied by 2 from the g. Then it's negative 4 and 4. Or we can write it in terms of the interval notation, where range of 2g equals to negative 4 equals to or less than y equals to or less than 4. 6.4. For which values of x will g into x plus 5 minus f into x plus 5 be less than 0 in the interval of negative 0, negative 90 and 0. So the interval that we are looking at is from negative 90 and negative 0. Before we can do that, the first thing that we're going to do is the following. We are going to now focus on g at x and f at x without that shift of 5 degrees. That shift of 5 degrees, it is our horizontal shift. In this way, we are saying we are going to start with g at x minus f at x. It's less than 0. What we do here, we can now transpose our g at x to the right hand side. It now becomes positive f at x. Then from here, what we now do, we do the following. We are going to check where g at x is less than f at x. In simple terms, we are checking a position whereby the f at x is on top or it's greater than the g at x. So where f at x is bigger than our g at x between the interval of negative 90 and 0. What do we see here? That means the f at x must be on top because it says greater than, and this one must be at the bottom. So f at x is on top here on those points right here. So what are these values to begin with? Remember, we work with symmetry to move from here to 19. So this will become how much? The x value will become negative 16. Right. So that will become negative 16 and 0 in this case. So initially, if it is just g at x and f at x, from looking at the statement, first, it is going to be 60 and 0. However, that g at x plus 5 degrees. So that means the first value, we are going to increase it by the 5 again. So when we shift it by the 5, so it's going to be negative 65 minus 5. Then we're going to have negative 65, and we're going to have the 0 again. On the f at x again, we are going to say plus 5 again. So that means even the 0, we are going to subtract 5 in both sides. So what we do, use the normal one. After that, we can see that this was altered with 5 units, shifted to the left. Remember, plus 5 means a shift on the left-hand side. Then it's negative 16 minus the 5, which is this 5 on the shift. And another one, it is our 0 minus 5. So that's why we have negative 65 and negative 5. Very important. First thing that we do all the time, work with the normal function, and we can alter at the end. Or now, the second way we could have written this one is we can use our interval notation. Says from negative 65 is less than or equals to x is less than or equals to negative 5. Now, let's look at 6.5. 6.5 reads as follows. Determine the values of p for which sin x multiplied by cos x will have the two real roots in the interval of negative 180 and 80. So we are given that sin x multiplied by cos x is equals to p. So what do we do in this case? We are now going to look at this in terms of we're just going to multiply both sides by the 4 right there so that I can work with a double angle. So we're going to utilize the double angle. So when we use the double angle, if I multiply by 4 both sides, I haven't changed anything. So that means I will have the double angle of sine for that part right there. So if I use the double angle of sine, why am I using the double angle? Because I want to have the ratio to be the same. Then we can now see, in this case, why I use the double angle. It leads me to our function right there. So our sine 2p is equals to, so we are going to see now our 4p is equals to what? It's going to be equals to plus or minus the 2 in this case, because now we are now looking at our g at x. So we are going to look at 4p as our function again. So we are looking for where are we going to have the two real roots. We are going to have two real roots at 2 and at negative 2. That's why we're intercepting how many times? 2 times, right? The 1, 2. If you go below that 2, you're going to intersect how many times? 4 times. If you go below that negative 2 again, we're going to intersect how many times? 4 times. So when you're looking for the two real roots, we are looking for points whereby we are going to multiply 2 times. So the 4p can either be 2 or it can be negative 2 in that case. Right. Therefore, we can now divide by 4 both sides. Then P can be 1 over 2 or P is negative 1 over 2. Now, grade 12, we have question 7 here. And for this activity, grade 12, you are going to be given 10 minutes to complete this activity. Now, grade 12, you can see that question 4, we are talking about 2D and the three-dimensional figures applying our trigonometry. So for this question, grade 12, you are given 10 minutes to complete the activity, and your 10 minutes starts now. Welcome back, grade 12. Let us now look at the question 7. Now, question 7, it reads as follows. It says, in the diagram, S, T, and K lie on the same horizontal plane. Okay, S, T, and K, they are in the same horizontal plane. RS is the vertical tower. The angle of depression R to K, so we have the angle of depression R to K, which is beta. And TSK, it is alpha, is given as alpha, and TS, it is P. Remember, you must be able to see those things on the diagram as you're reading them on our statement. And we are now given the area of STK. The area of STK, it is given as Q meter squared. Then it says 7.1, determine the length of SK in terms of P, Q, and alpha. Now, let us look at the length of SK in this case. How are we going to now find our SK looking at this one? Remember, we were given the area of STK in this case. Because we are given the area of STK, we can now use that and find our SK in this case. So our SK is this side. So how do we now work around this? Our area of STK is equal to 1 over 2 P, which is one side, which is included side of that angle, because we are going to look at the angle in the middle right there. And it's going to be half of one side, which is the side that is giving the included angle, and the SK, which is the other side that is giving us that included angle, multiplied by the sine of that included angle, which is sine alpha. Then we know that the area, it is Q. The side is Q meter squared. So it's Q is equal to 1 over 2P SK sine alpha. Then from here, I can solve for SK. When I solve for SK, I can divide both sides in by 1 over P sine alpha. And on the left-hand side, I'm going to do the same thing. So I divide it by 1 over 2P sine alpha, then divide by the same on the right-hand side. Then I'm going to simplify what I have on my left-hand side as now my SK is going to be 2Q all over P sine alpha. Or what you could have done here to make it easy, you could have just said Q, it's now going to be equals to 1 over 2P SK sine alpha. So what we can do in this case, we can multiply by 2 over 1. That's the first we can do. Then we get 2Q. It's equals to P SK sine alpha. Then we can now divide by P sine alpha. Then divide by P sine alpha. Then we can see sine alpha and sine alpha will divide, P and P will divide. Then my SK is now going to be 2Q all over P sine alpha, which is what I am having right here. So the easier way is just multiply by 2 over 1 first, and we can proceed with that, or we can divide by the whole of 1 over 2. However, it's going to be 2 over 1 again. Now, let's look at 7.2. 7.2 says, show that RS, it is equal to 2Q tan beta. Remember, we already have SK. We have found our SK, And also, we remember that the angle of depression, it is also equal to the angle of elevation. So I'm expecting that angle to be my beta right there. So to find my RF, I can use the trig ratio, I can use tan beta. So the first thing is RKS is equal to beta because the angle of depression is equal to the angle of elevation. And when I use my tan, so if I have tan beta right here, I have tan is equal to the opposite, which is RS over adjacent. So this is opposite over adjacent. My opposite is RS all over SK. Then what I can do from the following is the following. I can now cross multiply in this case. When I cross multiply my RS, it's now equals to SK times tan beta. After this, I can substitute my SK. When I substitute my SK in this case, let us see what I'm going to have here. When I have RS, it's equals to, I substitute the SK from the previous question. It was 2Q all over P sine alpha multiplied by tan beta. Tan beta. So you can see that tan beta will multiply with a 2Q. Then my RS is equals to 2Q. This is over 1. Tan beta all over P sine alpha. As easy as that. So we can see now this and that now we have proven it to be correct. Or we can use the sine rule here. How do we use the sine rule? We are going to say Rs all over sine beta. Remember our angle of RKS there, it is beta. So this, so it's Rs over sine beta. It's equals to, we are given SK, remember that. And what will this angle be? It's going to be 90 minus beta, which is our co-interior or area, interior angles of a triangle add up to 180. So that's how I'm going to get that angle, which is over SK. Then from here, we proceed from here. We are going to cross multiply. Then we're going to say RS multiplied by sine 90 minus beta. Sine 90 minus beta, it is the co-function, it becomes cos beta. Then SK multiplied by sine beta in this case. Then I can now divide by cos beta both sides. Then I find my RS equals to SK tan beta. So I'm going to divide by cos beta. I divide by cos beta. So cos beta over sine beta, it becomes tan beta. So it becomes a quotient ratio there of tan beta. Then I can substitute my SK in that space. Then I have my RS is equals to 2Q tan beta all over P sine alpha. Let's look at 7.3. 7.3 says calculate the size of alpha if A is less than 19, RS is 70, P is 80, and Q is 2,500 meters squared, and B is 42. The first thing that we're going to do here, you make it easy. Even if you are unable to find RS in the previous question, you can just use that from the question. Remember the question says, show that RS equals to 2Q tan beta over P sine alpha. If you are unable to show that, we can just take it from that question and we are working with it. RS is 17, so in the space of RS, I place in 17. Then it's equals to 2Q. My Q, it is given as 2,500, so I place in 2,500, multiplied by tan, our beta is 42, it's given as 42. Then I substitute 42 here, all over 80 sine alpha. Then how do we now get sine alpha as our solution? Then we are going to make sine alpha to be the subject of the formula. So what we can do in this case, we can now divide the 2 here, and we can now multiply by sine alpha over 1. Then we are getting 25 over 28 multiplied by tan 42. Then we can punch in a calculator. Then we get sine alpha. It is now 0.80. Remember, how do we work around this one? To make it easy, I can multiply by sine alpha over 1. So multiply by sine alpha over 1. What am I going to get? we're going to get 70 sine alpha. It's equals to 2 into 2,500 tan 42. Then we can just divide by 18. Then we multiply by 1 over 70. We multiply by 1 over 70. We get sine alpha. It's actually 2 into 2,500 tan 42 all over 80 times 70. So it's 80 times 70. So you can punch all of this in a calculator. Then you're going to get 0.80. There from here, remember we're looking for alpha, not sine alpha. Then you're going to take second function. So you're going to say alpha, it's equal to the sine of 0.8. Then we get our alpha to be 53.51. And they told us that our alpha is less than 90, and we get it as less than 90. And that is our final solution. Now, grade 12, that brings us to the end of our lesson. Now, for the next lesson, we are still looking at mathematics paper 2 revision. And on the second part of our revision, we are going to look at analytical geometry, which is mostly found in question 3 and question 4. And we are also going to look at our Euclidean geometry, which is found in question 8, 9, 10, and 10 in this case. Thank you. Enjoy the rest of the day.